ahead, Blake. Hmm? Yeah, since I'm doing part of the notes, and that way the people who are gone. I know. Okay. So the reason that I had you review factoring on your whiteboard today is because that's actually what we're starting with, except now instead of just factoring quadratics, we're going to factor polynomials. What's nice about that is all the stuff you learned from last unit still applies. So a lot of the same factoring you did last unit we can still do for this standard, even though we're dealing with cubics and quartics now. Okay, so I'm just going to read through some of this, but probably not verbatim. So this standard is an extension of last unit. At the end of last unit, we transitioned into writing polynomials. So like we were doing this x squared minus sum x plus product, those problems, and then we get cubics as answers. So that was our transition to working with cubics. These types of functions model other common real-life phenomena, so we do need to address them. And thankfully, many of the things that we do with polynomials are similar or the same to what we did with quadratics. So it's not a huge jump, and it doesn't look completely brand new. In the last unit, we talked about factoring and factoring patterns. With some particular cubics, especially, we need factoring patterns because they're the only way to get the solutions by hand. So almost all of math can be done several different ways. Like when we solve quadratics, you can use factoring, you can use completing the square, you can use quadratic formula to get to the same answer. However, these are some of the rare times when if we want to factor by hand these two situations, this pattern is the only way to do it. So we're going to cover those first and then discuss the other ways to factor, which will be more familiar. And don't forget what we've already learned. What was the pattern that we learned last unit for factoring? Sort of the D. Good, difference of squares. So difference of squares is still going to apply in this unit. You're still going to see it pop up every so often. So don't forget about that pattern that you've already learned. All right, so sum of cubes. Sum, what does that usually mean is in my problem? Addition, and then difference would be subtraction, right? Cubes is a term that you can take the cube root of. So, sum of cubes would look something like this, where you have two terms, and essentially they're being cubed in order to get that value that would be there. To factor it, we'd have to figure out what the cube root of a and b are, and then it would fit into this pattern. So to factor something that looks like this, you figure out what a and b are. A and b are the cube root of both those terms, and then you fit it into the pattern. Difference. Maybe. Difference of cubes looks like this. And what's nice is the difference of cubes pattern looks almost exactly the same as the sum of cubes, except a sign is switched. Okay, now before we get much further, I'm going to looking for a blank space here. Maybe at the very top of your notes, I'm going to make, or you're going to help me, make a list of numbers that have nice cube roots, because we're used to using squares and square roots. That's what we've been working with. But now that we're going to cubics, you're going to see cube roots more often. So the first number that has a cube root is 1. What's the cube root of 1? 1, because 1 times 1 times 1 equals 1. Okay, so cube root of 1 is 1. What's the next number that has a cube root? 8, because 2 times 2, or times 2 is 8. So the cube root of 8 is 2, because cube root means you multiply it by itself 3 times, and you get that number. So cube root of 8 is 2. What's the next number that has a cube root? 27, because 3 times 3 times 3 is 27. What's the next number? Good, 64. Cube root of 64 is 4. What's the next one? 125. Because 5 times 5 times 5 is 125. We'll do a couple more here. What's the next one? Or how would I figure it out? 6 times 6 times 6 is 216. So the cube root of 216 is 6. And then is 7 times 7 times 7 343? And then we'll go up to 8. What's 8? 612? 512? Okay. There's not going to be many times where your numbers are going to get much bigger than that. They usually stick between 1 and 8 with these types of problems. But just in case, if you weren't sure if a number had a cube root, you can always use your calculator to test it. The cube root symbol, or what you would use, is underneath the math button. And then if you look, it's the fourth option. So like if I didn't know if 512 had a cube root, or what the cube root of 512 was, if I didn't remember right offhand, then I could use that, and it would give me the cube root of 8. So that's always a good thing to use if you're not quite sure. But these are the most common ones, so these are ones that you should know probably by heart because we'll be using them often enough. All right, we're going to do 2 examples with these patterns together and see where we're at. We're also going, I didn't say solve, but we're also going to solve these at the same time. All right, let's stick with sum of cubes first. So, first one we're going to factor and solve is going to be 8x cubed plus 343. Okay, so if I tell you to factor and solve this, then you're first going to have to recognize, well, hey, I have a cubic because I have x cubed in my problem. That's my highest exponent. I have 2 terms and I'm adding. So if that happens, it's probably going to fit this sum of cubes pattern. Now, in order to figure out what A and B are, well, actually, before I do that, you do have to have these patterns memorized. So my suggestion is, until you have them memorized, that you write it down every single time you do a problem. So even though it's right there above it, I'm going to write it down again, because that's the pattern I'm going to be using. And then I always write what my A and my B are off to the side there. And A and B are the cube root of both those terms. So what's the cube root of 8x cubed? Well, what's the cube root of 8? 2. And then the cube root of x cubed is x, because x times x times x would give you x cubed. So A is going to be the cube root of that first term. So the cube root of that first term is going to be 2x. And then what's the cube root of 343? 7. Okay. Now, once you figure out what the cube root of both those terms are, you have your A and your B, and you just fit it into the pattern there, or the formula, if you want to look at it that way. So when I factor, it's going to be 2x plus 7, because that's A plus B. A squared. What is A squared going to be here? Be careful. 4x squared. Good. Because if you're squaring 2x, you have to square the 2 and the x. So you should get 4x squared minus A times B. So that'd be 14x. And then plus B squared, which will be 49. Now, if I'm solving this, at this point, just like with quadratics, you would take each factor and set it equal to 0. So when I set 2x plus 7 equal to 0, I get negative 7 halves as an answer. And then this other factor is a quadratic. Now, let me give you a few little hints about this quadratic. This factoring pattern will always produce a quadratic that you cannot break down any further. So it's not like we can factor this again. We can't. So the only way to solve this parenthesis is to use the quadratic formula. And that happens every time. That's just how the pattern works. So this will never be something you can break down more. So you'll always have to use the quadratic formula to solve it. So that's what we're going to actually do here. Quadratic formula is negative b, so we should have 14 plus or minus square root of negative 14 squared minus 4 times 49 all over 2 times 4. And then go ahead and simplify underneath the radical, and I'll take the first three hands that are up to tell me what's underneath that radical, what number it is. Do I have three? Anybody simplify underneath the radical yet? Close. What did you say? -588. 588? Yep. -588? Yep. Okay. Which means if it's -588 underneath the radical, I have a what? An imaginary. So I'd have the square root of 588 I over 8. And for this, you can just leave it like that. Okay. Now, question before we go to example 2. How many answers do I have listed there? I have actually 3 answers. I have the -7 halves, and then I have the plus version of this answer, and I have the minus version of this answer. So with the quadratic, you always have 2, or usually have 2, because those 2 answers always represent your x-intercepts, right? What's going on? All right. So, again, when we solve quadratics, we get 2 answers. They represent the x-intercept. So, with cubics, we get 3 answers always. And then you will have those also represent the x-intercepts. But in this case, how many x-intercepts do I have? Or how many could I plot? I can't plot 3. I have 3 answers, but I can only plot 1 because 2 of my answers are imaginary. So, we'll get more into that when we're graphing, but that's something to at least pay attention to right now. Okay, go ahead and flip to example 2. We'll do this one together, and then we'll practice a bunch of these on whiteboards to see how we're doing. Okay, so we're going to factor and solve this one as well. 64x cubed minus 27. Okay, we're going to factor and solve this one. Alright, again, if I tell you to factor and solve, you should recognize, hey, this is a cubic, so this is not a difference of squares. I have 2 terms I'm subtracting, so this is a difference of cubes. I'm going to write down the pattern from the previous page. Even though I know it's on the previous page, I can just flip back. I'm going to write it down until I know it by heart. And then the a and the b are the cube root of both those terms. Okay, so can somebody tell me what the cube root of 64x cubed is? 4x. Good. Cube root of 64 is 4. Cube root of x cubed is x. 4x. And what's the cube root of 27? 3. Now, don't look at that as like a negative 27 because the pattern takes care of the negatives and positives for you. So all you need is to look at the number and then find the cube root of that number. And here's your a and your b, so we're going to fit that into the pattern. So you have a minus b. A squared is going to be what? 16x squared. Good. A times b is 12x. And b squared is 9. And if I have to solve this, that means I have to set each factor equal to 0 and solve. What's going to be my first answer if I set that equal to 0? 3/4. Good. And then I always have to use the quadratic formula to solve this. And here's the other hint about this parenthesis, this quadratic. Not only will you have to use the quadratic formula to solve that, but you will always get imaginary answers. Yes, Lauren?
Why is it -3? Because you have to add it in.
Are you talking about this right here, why this is not a -3?
Yeah.
We just care about what the number is because the pattern takes care of the positives and negatives for us.
Well then, in the parentheses, it's like -3.
Right, because that's the pattern. So my b is 3. and then the pattern
Oh,
is
I see.
A minus B. Okay. Yep. So we're going to solve this using quadratic formula. So we have negative 12 plus or minus square root of 12 squared minus 4 times 16 times 9 all over 2 times 16.
Negative 432.
Negative what?
432.
Negative 432?
Yep.
Anybody else punch that out yet? I just want to double
Yeah.
check. Yep, okay. Which means I have another imaginary, which will always happen. And we can leave it like that at this point.
Can't you simplify the 12 over 32?
You can't unless this broke down, this 432 broke down, and then you'd have to simplify all three. Okay. Now, you can see where we're headed. You actually know how to do each one of these already. It's just kind of thinking about it in terms of cubics. So, since this is the stuff that we haven't quite done yet, really, we're going to practice these right now. If you would get out a whiteboard, a marker, and a rag. I'm going to give you a bunch of these to try.